right, so let's get started. Our first speaker of the day is Motoo Suzuki. Motoo Suzuki.
Motoo is correct, but I don't know.
Motoo, okay. You put two O's. Yeah. All right, so Motoo Suzuki, we are very happy to have. And he will tell us about a spontaneous and explicit breaking of the -1 symmetries and its connection to the strong CP problem. So whenever you're ready, please take it.
Thank you. First of all, thank you for inviting me, and I'm happy to be here. So today I want to talk about this kind of topic. But 3 years ago, I was in Boston, Harvard, and I heard about the talk by the hot tag, and then he talked about the non-invertible symmetry stuff. And then at that time, honestly I didn't know anything about this kind of topic. But then I got interested in the generalized symmetry. And then fortunately, the matrices know about this kind of topic, and then I could join these topics. And fair complaint, I'm trying to apply the generalized symmetry to the particular phenomenology. But fair complaint about this kind of stuff is what's new. I always ask about this kind of question. I could do that without knowing the generalized symmetries. But in my mind, I always think that if people already know that this is completely useful or completely new, and then this is already too late. So to find something, I think we have to jump in something unknown field. So this is my mind. Okay, let me move on to the physics. And then today's talk, I want to discuss about the strong CP and its solution and its connection to the generalized symmetries. Why this is interesting? I think that one of the biggest problems in modern particle physics is to close the gap between the effective flow energy theory and the high energy theory, which is something unified one. And to close this gap, I think it's from bottom-up approach. I think it's important to focus considering about some small. Sometimes it is important to consider some small cracks in the standard model. We already know the big issue in the standard model. For example, the dark matter or baryogenesis stuff. But now, but here I am focusing on the strong CP problem. This is a problem between the kind of inconsistency between the theory prediction and the experimental. Theory predicts the naively the order 1 parameter, but experimentally this parameter must be much smaller than 1. So this looks a small cracks. But I think that these small cracks may be able to close this gap. And today, I want to try to close this gap in terms of -1 symmetries. Okay. And we already know that one elegant solution to the strong CP problem is the axion solution. But axion solution itself still has some small cracks. It is known as a quality problem. What's the quality problem? I'll explain more detail later. But so if we consider the quantum gravity, then every we know that there's a conjecture no exact global symmetries. So action constructed by using some U1 Pechak symmetry, global symmetry. And then this action potential itself is not protected by anything. So usually the original action potential from the QCD is disturbed by the quantum gravity effect. I think this is, but this depends on the how we consider the UV theory. So this might be the small cracks, but I think still this is important to close the gap. And then today I want to also discuss the quality problem in terms of this -1 form symmetries. Okay, then today's outline of the talk is first, let me briefly review the strong CP problem and its solution. And some action cosmology stuff. And after that, I introduce the -1 form symmetries. Then I want to discuss the spontaneous symmetry breaking of this -1 form symmetry and also the explicit breaking of it. And then by using this understanding, I want to discuss about the quality problem. Also, if I have a time, I want to discuss some, show some my ongoing or recent work. Okay, let me review the strong CP problem. Okay, let us, maybe many people already know, but for computers, let me review this. Let us consider the QCD, and in QCD, we know that there's a called mass term and so-called theta term. This theta term, as we know, breaks the P and CP symmetry. And from this, in this Lagrangian, we may consider some chiral rotation of the quarks. And then we know that this theta phase and some phase, overall phase of the quark mass is related. And the physical parameter is so-called theta bar. It is given by the combination of this theta and the phase from the quark mass. And now MU, MD is the 3x3 matrix in the type quark mass matrices of uptype quark mass, and MD is for the downtype quark mass. And from the experiment, from the neutron in-game experiment, this theta bar is try to observe, and there's upper bound for this theta bar. Then this theta parameter itself is there's no way to naively that this theta parameter itself is the order one. So that immediately it contradicts this 10 to minus 10. But let me explain a bit more about this. So the experimental constraint for the neutron electron dipole moment is this one, and let me naively estimate the neutron EDM. EDM is classically speaking, this kind of plus and minus and the distance. And then in QCD, this distance is naively the 1 over lambda QCD. So theory is very naively the 1 over QCD, and we know that this is proportional theta, and then from the last statement, the experimental this must be less than the 10 to minus 26, but rarely naive calculation 10 to minus 15 times theta. And more concrete computation is also gives a similar order of magnitude. And then this immediately tells us that this theta must be less than the, theta bar must be less than the 10 to minus 10. And this is quite small, and we want to know the why this and I want to know the why this is small. And let me also still explain that why this theta bar smallness is kind of strangely small, because model building point of view, this theta bar 10 to minus 10 is quite is strange. Sorry. Model building point of view, this is can be this smaller theta bar is kind of fine tuning. Problem. So let me explain this. So we know that the CKM phase is order 1. This means CP symmetry is maximally broken. And naively, if we want to get the order 1 CKM phase, we assume that the quark mass matrices, including some random, some order 1 phase in the random position. So the MD is including some order 1 phase. However, if I consider this kind of quark mass matrices, because theta bar is coming from the combination of this theta of this one, so this gives us some theta parameter plus some order 1 number. But this must be small to the 10 to minus 10. So I need to tune this theta to avoid this constraint. So this is nothing but the fine tuning program. Okay, so I think I can convince how this CP problem is important and strange from the point of view of particle phenomenon. Oh, sorry.
That works much better. Yeah.
And then we want to solve this strong CP problem, and as we know that there's already solutions. The famous one is the axiom, which is the dynamical solution. And also we could consider some CP symmetry solution. Basically, there is a paper about some CP symmetry model doesn't work, but I'm still confused. So if someone knows, I want to discuss later. Also, sorry, some massless scope is also the solution. Nice. And there are many other approaches, I think. And then first, let me briefly explain about the axion solution. This axion solution is briefly speaking, this axion solution is change the original theta parameter to some dynamical. This means originally this theta is just a parameter in the theory, but now I change this theta to the field. So this theta is already appearing in the measure of path integral. And then what we know is the potential of this theta x, the axion. Is this, roughly speaking, this kind of cosine potential. And then this potential has a potential minimum at the origin. So dynamically, we can set the theta parameter in below. This is a strong. This is a one solution. And yes, sorry. And the concrete model of the action is there the many way, but one realization is providing this action from the phase of the complex scalar field. This is so-called the PQ field, and this PQ field getting the wave, and the phase direction is corresponding to the axiom. And we assume some U1 Pechak symmetry because of that. This axiom is almost non-Boson boson, but this axiom is because of the anomaly of with color. This axiom is can get a path of this kind of thing and should non-Boson boson. Okay, this looks the axiom is already solution and we don't need anything. Okay, we're satisfied. But I want to emphasize that there is some still the problem, the quality problem. So here the axiom is generated from the phase direction phi. But if we expect the quantum gravity breaks the global symmetry, so I could allow to consider, for example, this kind of potential. In Planck is Planck mass, and this is applied to the fifth. And the problem of this potential is that this potential is also affects to this original potential. So the original potential was only coming from the QCD. But now this term is provided another potential. Here the epsilon is just a dimensionless coefficient, and VPQ is a vacuum rotation value of phi. And this delta is coming from the phase difference from between the Q3 term. So this phase is coming from this coefficient. And then what is happening is originally this potential is minimum is the origin, but because of this term, this can be this so the actual minimum can be restricted by roughly theta, roughly delta, and then the potential is I don't know if I include many terms or drastically change. And how but if this epsilon is small, I can avoid this problem. So how this epsilon must be small? The rough estimation of this shift of the theta is can be done by comparing this potential and the original QCD potential. And to be consistent with the experiment, I require that this must be the less than 10 to minus 10. And typical value of VPQ is, for example, the 10 to 12 GB. So if I put to this, so this naive estimation tells us that this absolute value of this epsilon must be 10 to minus 15.6.
What sets the Petchy-Quinn value? 10 to 12.
10 to 12 GB is coming from to explain the dark matter abundance, for example. Yes. I will also explain.
There is a range.
There's a range. Yeah, sorry. So just
There is a allowed range.
yeah, there's a allowed range. So the precisely speaking, the this is allowed range.
Okay, but none of these values fix this because this term is kind of forced on you in the effective field theory, and then you need to explain this shift delta being small by another fine tuning.
Yes. So
It's like the same.
yeah. Yeah, even if I take this lowest value, that this is still correct. And then this epsilon is must be extremely small. So this is we may say that this is again that this is another tuning problem or strong shifting problem again. So this is crazily small.
Upper bound.
Upper bound VPQ is just I take a plant once.
Yeah, but no, I thought it was a lower bound.
Sorry. Lower,
Sorry,
lower.
lower upper bound.
Oh.
Not the upper bound, but
Lower.
a few orders of magnitude.
Yeah, probably there's a subgroup. Yeah.
Yeah.
Oh, yeah, sorry.
If it is too large, weakly coupled, and we can modify the cell evolution, and there's a bound. That was roughly 1.
That was 10 to 12,
Yeah, that was probably 1.
So can
Sorry, 10 to the 12 is coming from the dark matter.
yes, 10 to 12 is sorry. So this is not a bound.
Yeah, this is abundance assuming generic initial misalignment.
Yes.
Right, the 10 to the 8 is.
Is that abundance star?
Because if you're strong, couple too strong, you will right. Sorry, you're emitting axioms. Yes, right. That's like star wave if you're emitting axioms, right? And they'll just escape. That's
Yes.
Yes.
Thank you. And people are, of course, already tried to solve this quality problem. So let me briefly explain what kind of solution people consider. One naive, kind of simple solution is just to consider some gauged ZN symmetry. So originally, this phi is not protected by anything. So I could write the this kind of potential. But if this phi is charged under some then symmetry, then only this term is allowed. And then if n is this d n is roughly the 9 or 10, and then we can avoid the strong CP problem. Also, so along this line, we could also use the some U1 gauge symmetry or some non-abelian, for example, SUN gauge symmetry. And other possibilities, for example, using the conformal dynamics, or of course we could the extra action from the extra dimension is a one simple nice solution to this kind of quality problem. While I don't discuss today. Yes.
So you can only why you need two gates there, because if you assume the same symmetry, they will have the term prior to the end. I guess you repeated it because you want to avoid another kind of quality.
Yes. So you say that the global GM is the
global GM can already do this.
Yeah, that's how to say. I don't understand quite why global GM symmetry can avoid. I think global GM symmetry can still explicit problem.
Oh yeah, I mean that's another kind of quality problem.
Yes.
Yes. Yeah. Okay.
Yes. Okay, so now I'm focusing on the action model, and then I show that there's a quality problem. Then the action solution might be not good. So we could consider the other solution. For example, the Nelson-Mann type model. So let me briefly explain about this because I mentioned about this also later. So this solution at the high energy scale, the theory is CP symmetric. So because of this, I could avoid the appearance of theta GG children. However, we know that the CKM is order 1, so I have to break this CP symmetry. So at some intermediate scale, I introduce the spontaneous CP breaking of CP symmetry. And then I need to generate this CKM is order 1, but I have to be careful about this SSB of CP doesn't generate the large data amount. One simple concrete model is the forms. Just we introduce the one pair of vectorized clocks and also introduce the complex color fields which break the CP symmetry spontaneously. This QQ bar is additional vectorized clocks, and this M is some real mass. And then this A is just a coefficient, dimensionless coefficient, and this eta is break the CP. And this term is just communicating that this Q vectorized clocks and D bar is standard model downside clock. And so why this setup is good? Because if I look at the tree level clock mass terms, the quark mass term is formed, downtown quark mass is like this. So this M is just a vector-like mass, and A eta is coming from this mixing term, and then this Y is the usual equal term. And because this is 0, so if I take argument determinant.
Sorry, little Q appearing the last detail is actually like.
Sorry. Sorry, this is standard already. So we don't have this kind of term. And then we could avoid this kind of term, for example, introducing some U1 of them symmetry and then at the tree level, this doesn't produce the correction to theta bar. So the question is what is the relative correction to theta bar? And in this type of models, there's one contribution to theta bar, and then the library we need this A must be less than, roughly speaking, the 10 to minus 10.
So here, all the parameters are real parameters.
All the parameters are real parameters. And then because of some potential of eta, this can get some complex space. Okay, then, but still this kind in this kind of models, we have a quality problem because I forbid this kind of term by using this same symmetry, but for example, I could still write down the this term is still allowed. And this term is appearing here, and then this starts to generate the non-zero theta bar. So we have to forbid this kind of stuff. And if this term is small, it's fine. So this put the bound of eta is roughly 10 to 8 GB or something. So I just want to say that even if we go to the other solution, we encounter the quality problem, and still this is, I think, problematic. Okay. And for completeness, also, let me very briefly explain about the cosmology of the axiom. We have mainly two types of scenario. One is so-called the plane inflationary scenario. In this scenario, before the end of inflation, during inflation, PQ symmetries and temperature become lower and lower, and around the TQCD, action potential is generated. And at this time, because potential appear, the action starts to oscillate. Around the X origin. And then this oscillation is behave as a matter, and this becomes a dark matter. And if we to explain the whole dark matter, correct dark matter abundance from this mechanism, FA is around 10 to 11 to 10 to 12 GB. We also have another scenario, a so-called the post-inflationary scenario. This case, PQ symmetry is break after the reheating. So first, PQ symmetry is restored. So
In the pre-inflation scenario, is there a bound on the reheat temperature?
reheating
Oh.
from the axiom, for the axiom.
Yeah, okay. I was thinking that if we heat up the universe beyond the PQ, sorry, never, no. I was just wondering whether you can restore the symmetry after that, but anyway, I guess PQ scale is way higher than B. This example. So if we don't
Yes,
have
sorry,
that-
yes. So I assume. There is some subtle scenario, I think, between the reheating and the end of inflation, there's some matter domination error. And between this region, PQ might can be broken, but I don't know this case where. Yeah. And then this case is first PQ restored, and at some lower temperature, the PQ symmetry is broken. And then because this is spontaneous breaking of the symmetry, cosmic string will form. And then temperature around the QCD transition scale, the domain model is formed. And depending on the action coupling to the tilde, there's some type of scenario. This LTW is the so-called domain number. Roughly speaking, this is the this is the DG tilde term, and this theta physical domain is 0 to 2 pi, and then this LTW is so-called the domain number. And then if domain number 1, this kind of first we have a string, but if domain number 1, the domain wall responds like this. So this boundary is the string, and then inside the domain wall is formed. And this system is unstable because there's a domain wall tension. So this can shrink and go into nothing. And this and also I could say that because of this NDW1, there is no GM global symmetry, so there is no domain wall form. And then this case is axiom decay constant is a bit smaller than this FA. So roughly speaking, this is around the 10 to 11 dB to explain the action diagram. Also, another case is the domain number is larger than 1. This case is there's a string and the NDW domain wall is attached to the one domain wall. So if this is a domain wall number is 3, for one string, the 3 domain walls are attached. This configuration is stable, and and this causes the so-called domain wall problem. Because if this dominates the reverse, universe become much rarely inhomogeneous, and we don't know what happens. Okay, so and if we want to solve this kind of scenario, people start to introduce some explicit breaking term for PQ. I mean, explicit break. This is coming from some global ZDW, ZNDW symmetry. So if I break this symmetry explicitly, I could solve this problem. But this is also produce a kind of quality problem something. So yes, and also there's another interesting scenario is so-called using the Lazarus-Staffy mechanism. The Lazarus-Staffy mechanism is identifying this case is there's some NDW degenerate vacuum, but this degenerate vacuum is identified, for example, the some center symmetry of SUN gauge theory, for example. Some continuous symmetry can, if some continuous gauge symmetry can identify the discrete vacuum, it may solve the domain model problem. But as long as I know the lateralization mechanism, is still people are studying, and the actual problem is the dynamical problem. So I think there is no clear simulation for this lateralization mechanism. So still this is unclear if you can solve the domain problem. Okay, anyway, this is a review of the strong CP solution. And let me move on to the -1 form symmetry.
So for the case of MDW equal to 1.
Yes.
So for example, if it is just really coupled to pure Yamils and that domain wall is associated with CP bracing of Yamils at theta equal pi, then yeah, Chan-Simons is living on that wall, and chiral current has to support, give a opposite tension of the action string, so it cannot really negate that.
That's
Yeah.
interesting.
Yeah.
So I can't understand also.
So yeah. So I think to understand. So what is really the assumption for the annihilation of this single wall?
What is really assumption?
Or what is the argument?
Sorry, the inside the wall,
Yeah.
right, and that equals 1. Inside the wall, theta goes from 0 to 2 pi.
Yes. Okay.
So what is the argument again?
So basically, when connecting theta equals 0 and 2 pi wall, then
Yeah.
Chan-Simons theory is induced on the wall.
What does Chan-Simons theory do on the wall?
So basically, so wall also has a boundary, right? So if boundary supports nothing, Chan-Simons itself is not getting value.
Right,
So
right.
chiral fermion should live on that
That's
boundary.
That's right.
Then that gives a current. And if it's too small, it gives the 1/L type energy. So yeah, tension is proportional to L, so it wants to become shrinking.
Okay.
But 1/L gives the opposite.
Right.
So there is a
I see.
finite.
I see.
So yeah, that is what Zohar called pancake value.
I see.
Yeah.
Oh. I think that sounds right. So here, I guess the argument was likely that the string tension is much like the domain wall tension. So I mean, it's just like a rubber and trying to shrink and then destroy. But you're saying that as it gets smaller because of the chiral current, it gets counteraction.
Yeah.
And then you're saying that makes stabilize.
Yeah.
Sorry.
Yes, from that. But in general, it wouldn't. It will make the chiral come out when it's getting variables. Yeah. Now I wonder if the point is that in the QCD rather than the Purian, I really think that there's no room there.
Yeah.
What is it correct? But if QCD with a fundamental part rather than that,
Yeah.
then probably I wonder if you can avoid the argument of a transcendental division of the wall and the chiral current counterbalance.
Yeah, that depends on, so depending on parameter, maybe that's true.
Okay.
Right. Yeah. But if Hessian queen scale is much larger than lambda QCD, then I would think there should be a chance sign.
Well,
At least in the core of
the
this.
wall is only made at this QCD center. Otherwise, there's no wall.
Okay.
There was a PQ scale, you get string, and this and then QCD, you get the domain wall.
Yeah.
Now, for all the way down to the QCD scale, it's the QCD rather than Purian scale.
Right.
But then-
So what I said is, so it depends on the mass of the core.
yes,
Yeah.
less than the lambda QCD.
Yeah. Yes, but then there should. Yeah, but that's
Actually,
debatable point. But
I agree. I haven't heard this argument before. Okay, anyway.
I want to first grade.
Yeah.
Okay, let's go to the more crazy stuff. So this is the minus one from symmetries. So this is not too crazy, but not so robust. But let me try to do that. Yes. Okay, so you may already hear or you already know, but let me start to explain about the ordinary zero form or free form. Yeah, just a very quick. So ordinary zero form symmetry case, this acts on the local operator. And we know how there is a conductive charge. P form is P form symmetry is similar stuff, and this acts on the extended delta. And we also have a topological operator. Then now I want to, this is ordinary symmetry, but I want to discuss the minus one form symmetry. So to try to understand that, let us consider that okay, so zero form symmetry case, this acts on the local operator, and for the charged object, this are making the line. And the one form symmetry case, this acts on the line operator, and for the charged object, this is the object, this is the surface, make a surface. And then higher form symmetry. And in this line, if I consider the minus one form symmetry, I don't know what kind of operator this acts, but for the charged object, this seems to say that some point-like object, this acting on.
What that charge object mean?
Kind of, so for example, the kind of electron stuff is make the one-dimensional world line.
What give me the word line?
World line. Sorry, world line. Sorry, world line. Yes, yes.
The operator is simply the point line.
Oh, point line. Sorry. Yes. I think. And then in this line, this is point-like object, and this is corresponding to the as I try to explain later, but this is corresponding to the instanton. But this instanton is not living in our world. This is only can be found in the Euclidean spacetime. So okay, I agree that this is quite different from the usual symmetry, but at least if I start to understand in this way, there is some makes sense. Yeah, we have some equations or something which makes sense. How strange the minus one form symmetry? Let me continue to explain. So first, let us try to naively consider the topological operator for this minus one form symmetry. For example, T equal 4, space-time dimension is 4. Then So this is instanton, the symmetry related to instanton, and finally this is a symmetry of the related to the conservation of instanton number. So naively, this is the topological operator, but this is quite strange. First of all, in D equal 4, this is already the top form. So if I understand this is current, and then this is top form, so D of top form is always equal 0, and that doesn't tell us anything. So this is already strange. And this doesn't make real sense. So, but we may try to still define this kind of stuff by considering the background, introducing background gauge field. Before that, let me remember about the zero form symmetry stuff. Gauging zero form symmetry is there's a current, and then I couple this current to the gauge field. And zero form symmetry case, this is one form. So in this way, naively, I could do that gauging minus one form symmetry. Not the gauge, sorry, background gauge. Symmetry, this doesn't, I said that this doesn't make sense, but yes, use the press FHF, and then I introduce some kind of background gauge field. One form case, zero form symmetry case, this is one form gauge field, but this case is zero form gauge field. And this already looks like an action potential, and really this is related to the action stuff. But let me try to write down the more a bit precise, more generic definition of the minus one form symmetry.
I have a question.
Yes.
So, say I just place the rule of A in the 0 points. So, can we say here, theta is has to be periodic?
Yes. So I will explain soon, but yes, this periodicity is including in the definition of this one. And this theta to theta plus 2 pi is we can regard that this 2 pi is large gauge transformation. There's no local gauge transformation, but this is kind of large gauge transformation.
Or minus one form symmetry. Only doing this by assuming theta.
I don't know if this is the only way to define the minus one form symmetry, but what I could do now is this.
So still minus one form symmetry to apply potential rationalized form, or
I think so, yes, yes. So for precise, I just write down. Yeah, this is almost same to what I said, that now I am saying that this theory has a minus one form U1 symmetry. This U1 is, we use this U1 because this trace, integration of this trace FHF is integer. And then we say that this is minus one form U1 symmetry if the kind of current can couple to some periodic background gauge field, some theta x. So yes, so this is what I can do now for now. And then, so of course, this includes this trace FHF case, and as I already almost explained, but this star J0x is corresponding to trace FHF term to FHF term. Yes.
If you can't fix solid for periodic field, would you say it has an R one minus one?
Yes, that's yes. So yeah, that's minus sign. So so this case is I said that this theta bar theta plus pi, but so how to say? So every top form can be regarded as a minus one form symmetry. But in this case, the integration of current doesn't. In general, this is not a integer, and then we call this is R minus one form symmetry. But I don't know how this is. Yeah, compared to this one, I don't know how to consider this kind of stuff. And then, yes, sir. Yeah. And how say gauge? Sorry. Maybe I think that one of the nice trial for this R minus one form symmetry is considering some classical conformal symmetry. Classical conformal symmetry case is which is like a UMPQ. Classically, this is negative, but relatively this is broken. And then this trace FHF term is corresponding to some trace of energy momentum tensor. So this case might be comparing the PQ symmetry. You may say something, but I don't know it. I don't know it. Yeah.
Following on from this question, if you have theory with a fraction distance off, would you still have a U1 symmetry or change? So then integral over f plus f is not just integer, right? It has a lower over n type of fractional.
How to say? Yeah, I think still we can say. I mean, if we kind of this is change of normalization stuff. So
okay, because the theta just gets extended to 2 pi n rather than 2 pi.
But still
view it as a U1 state.
Yeah, I think, but I don't know. Yeah, maybe we need a more precise name, but
okay.
Yeah, so far I think this.
Can we say Lagrangian is the 1 minus 1?
Yes, yeah, I think actually that work is by buffer and J.
Really?
So Lagrange. So if I allow this kind of stuff, and then every term is the minus one conservative current, so every coupling can be regarded as a kind of background ratio.
The H bar is
every constant is every coupling is yeah, so must be something. Yeah, that's a minus one here if I miss.
Probably want something that's exactly marginal.
Okay, that's the I'm sorry.
Yeah, you don't want the charge to sort of shift with scale, probably. So probably you want some sort of homology class, that doesn't depend on like local metric measurement. That would be sort of the analog of having a homological.
Maybe I say so.
It's just saying the f doesn't change in this case.
I see.
Because Lagrangian doesn't have changes in the state.
I see.
We normalize. You need a conformal.
I see.
For curious, they don't want the charge to change with the state.
I see. So, okay. maybe this is more.
But I think the question is what you get out of it. Okay, let's maybe not die on this definition.
Would you say that a free Dirac fermion has a minus one form symmetry at 4D? It has a mass parameter which could be complex.
Minus one form R.
Well,
You are.
say you want.
I don't know. I can minus one form U R. Sorry, the question is, do they have some?
There's a kind of a silly periodic coupling for just the phase now.
So yeah, here, but I said that this is linear. Yeah, but yeah, that's the good point.
But let's see what you.
Yeah,
Okay.
okay. Sorry, this is I almost also say that a way of gauging is making this theta is dynamical. So this is nothing but the axiom. Okay, so I think I could finish the definition, kind of definition of minus one form symmetry. So let me move on to the spontaneous symmetry breaking of the minus one form symmetry.
Motoo? At some point, you're planning on taking
Then
after this?
if I okay, now maybe.
Up to you.
Yeah, because this is a bit long.
Okay, so it's
Yes,
it's 10-minute break, okay?
Yes.
Okay, so let's take a 10-minute break and then we will resume at in 10 minutes. Okay, let's resume. Okay, let's get started again. Please come in. Anyone else? All right.
Thank you. So let me move on to the spontaneous symmetry breaking of the minus one form one symmetry. I also want to talk about explicit breaking, but I'm not. Maybe I try to do that. Yes. So the main statement in this SSB is that topological stability is a kind of a useful order parameter for this minus one form one symmetry. Topological stability. Topological stability is defined as theta is a theta parameter of theta, and V is a vacuum energy. The second derivative vacuum energy is corresponding to the topological operator. And then we want to say that this is the order parameter for the SSB. So to see how this statement makes sense, let me start to consider the 2D Maxwell theory. This is just F is just a field of strength into the Maxwell theory, and this is kinetic term, and this is corresponding to the theta term in QCD. And from EOM, we got this one, and also we also have a Yang. And then this is corresponding to the electric minus one conformity symmetry. And this is in 2D, this is nothing but the minus one related to the minus one conformity symmetry. This is like this F is like a trace F. Okay, then let us study this model. In this to the Maxwell theory, there is no propagating degree of freedom for the photon, because in 4D we have a transverse mode, but in 1 plus 1D there is no transverse mode, so there is no propagating degree of freedom. And then, but still we have a zero mode, which we find out. And now, now I'm considering the space is compact by less one, and this is R is the radius of this space. And then in terms of this zero mode, effective theory of this 3D Maxwell theory is given as so this is basically the 1D quantum mechanics. So if we want we want to quantize this theory, then the conjugate momentum is given by the and then the Hamiltonian is as usual, we could find energy eigenstate in this theory. Then the energy eigenvalue. And the ground state is yes, basically this is equal to 0. Then in this theory, I could consider about the topological susceptibility.
Wouldn't ground state depend on the theta?
Yes. Yes. So topological susceptibility is as I already showed this here, this quantity, and then because this E is depending on theta, then this can be non-zero. This become non-zero. So what is saying this non-zero topological susceptibility? So this topological susceptibility can be written down as in this 2-point coordinate function and some integration, and I could deform this equation is like this. So this F is field strength, and this is corresponding to the minus one symmetry, and this F is kind of this F is total derivative. So because of total derivative, so let's say I could define this way, and then this derivative part is if I modify this equation, then this derivative part gives this momentum, and then remain this KU. This is 2-point correlation function, and then we know that this is non-zero from here. And how can we understand is that because this is non-zero, but here we have a 2 Q. So to make this is non-zero, we have to have some 1/q² massless pole in these 2-point functions. So we interpret this massless pole as a non-Bogolson field for the minus 1/1 symmetry. Here I am saying this is field, not a boson, because there is no propagating degree of freedom. Okay, yeah, it is. At this stage, you can freely say that this is non-Boltzmann field or something. But let me try to check that how this makes understanding makes sense. No. Yeah, so agree. So simply say that because of this 1/q², I just say that there's some yes. So I don't say that, yeah. So question is yes. So far that
Usually, ordinary symmetry breaking, and bottom is scalar here. So if one form symmetry is broken, that is bottom is one form. Then in this case, minus one form symmetry breaking,
yes.
the bottom should be the minus one form.
Oh, the dual is the 3 form. For the case dual is 3 form, and dual is
Dual.
yeah.
It's not even the particle. Yeah.
Yeah, so kind of, yeah, I understand the dual also. Okay. Okay, so let's try to base this minus 1 form symmetry and what happens. To gauge it, I introduce the axiom. So now the theory is so in this theory, now this theta is become an unphysical parameter because theta is unphysical because I could change phi. I could shift phi phi plus some constant, and then this theta will become to the theta plus c, and this is indicating that this theta is unphysical. So the theory now doesn't depend on theta. So if we compute the topological stability, this is zero. And this is saying that so this is saying that originally we have a pole, but once we gauge this minus one of symmetry, this gauge field kind of eaten this energy field, and there's no pole anymore. So also another consistency checks that if I start to introduce the mass term for this phi, then this theta becomes physical, and then we and theta is not unphysical. Again, theta becomes physical parameter, and we have a SSBO minus one.
This is 2D version of massless fork solution versus if you use the mass.
Yeah, yes, something like yes, because DR to Z, yes. Okay, then maybe for some people almost clear, but let me go to the 40 theory. For example, the SN theorem is 3. Yeah, so this is almost saying that in this case, the topological stability is almost similar, but the topological stability is now given by this K mu. This K mu is if theta is total derivative, so this K mu is nothing is quite similar. Behavior is quite similar to this case. And if I could go to the low energy theory of this theorems, and I think in large limit, this theory can be written as a C-form gauge field. And then if we go to this form, this is quite similar to the 2D Maxwell theory. To the Maxwell theory. And in this picture, if I introduce the axiom, and this axiom is dual to the two-form field, and once we introduce we find that this is sorry. Once we introduce the axiom, we have this kind of term. This looks like a Stuckel-Belk mass term, and this is another makes sense evidence for the SSB of minus one for muon symmetry. Also, we could also consider of some kind of a dual electric Higgs phase and dual to the magnetic confinement phase. And if I consider some SSB of gauged E10 form symmetry, this is related to some monopole and spring. But this minus one form case, if once I gauge, this is string and wall. So this kind of correspondence is also we are having. So by accumulating these kind of make sense facts, we state that this topological stability more generically the vacuum energy when it's depending on theta, then this is indicating the SSB of minus 1 form symmetry.
Example where you have a parameter or -1 form symmetry that's non-trivial, that is not spontaneously broken. So like this example, you just say, oh, I have a -1 form symmetry, but I just shift it away by having a few.
Yes.
But
Non-SSB case.
Even when there is.
yeah, when it can't just be shifted away by something.
Sorry, so this is not so you are saying that when this chi is 0.
I'm asking
Okay.
if you have an example where the vacuum energy is independent of theta, and theta is a physical parameter.
For example, if I consider the much higher temperature compared to the QCD, then if condensation doesn't happen, then I think vacuum energy now doesn't depend on theta.
So you mean like you have Banks stacks, like gauge theory?
Sorry.
So you're asking about like if you're saying like you have Banks stacks, like gauge theory with the theta term.
Oh, but that's not those permanents.
Oh, okay, so yeah.
No, I think, did you say high temperature? You said high temperature?
Yeah, high temperature, yes.
You mean infinite temperature?
Yeah.
Yeah, infinite temperature, maybe, yes.
That's
So-
a little bit singular, right?
Okay, yeah.
Finite temperature.
Yeah, okay. So, yeah, so in this sense, this is not a good example, yes. Sorry, I need to consider. Yeah, same, yeah. Yeah, just, yeah, I need to correct.
Usually when they have broken, then the ground pitch has some delay. For their home gate, there is some
Yes.
delay vacuum and also the high frequency that is proposed order. And what happened in this case? Is there any delay?
I never considered that. Yeah, I see. Thank you. You have something you say in mind, something.
Yeah.
Oh,
Yeah, just a question.
yeah, thank you.
Another question.
Oh, yes.
Is there an analog of having, so you have a continuous symmetry. Normally you can add couple to a background gauge field. And if you couple to a flat background gauge field, then you don't, like something topological, then you don't produce any vacuum energy.
Okay, yes, okay.
I was wondering if there's an example or an analog of that for one form.
And even if I include, so it is similar, even if I state some constant or some, we say.
Well, I don't know, I was trying to understand this better.
So let's say if you have a serial, say that only coupled before.
Okay. Say the couple to the only.
Only say that coupled.
Oh, okay, yes. Okay, I see. And then, so this case is a result monopole. This,
That
but this doesn't have a,
does vacuum energy depends on it.
no, like, if there's no monopole, I think.
Also, theta may not be physical also.
Yeah, so this case is just theta dependence disappears. So
That Maxwell
Yeah.
it's just a Maxwell.
ground state energy doesn't depend on theta,
Yeah.
at least on R4. Yeah.
Yeah.
Yeah. On non-trivial.
In this case, there's still something, yes.
It
So
does.
I think that vacuum energy defined in some flat.
But correlation function in general. Correlation functions with full point operators.
Oh, we extend it out.
Yeah. Not particles.
Okay.
So I'm trying to say the theta is a physical parameter. Otherwise,
so even in this case,
even in this case, yeah, theta in Maxwell theory is a physical parameter. Even though the vacuum energy doesn't care about it. That would be an example.
I see.
Was asking that question.
Oh, yeah. Very good.
I don't know if I would refer to this.
Also,
How do you want to?
following up on your question, you're asking, usually we have if we have a spontaneous broken lower symmetry, we have particles on the back, right? You're asking that. I wonder if there's a degeneracy of the notion in that equation. So if we had a spontaneously broken minus local symmetry, vacuum structure, someone has to satisfy that equation. I wonder, he took it as a definition of it, but at the same time, it's a constraint on the vacuum system, right?
Right.
I don't know if it's a chicken and
I think
egg, chicken.
This is the order parameter.
I understand that.
There's nothing to parameterize the vacuum magnet. That hasn't been identified. No, like axiom. There you have the degeneracy. There's someone going around.
I mean, the way I understood why this is a good order parameter is because this is how you get the gated field.
Yeah.
Like, this is literally
Yes,
completely
yes.
Therefore, this is
Yeah,
this is
yes,
the corresponding to the
yes,
spontaneous problem.
Yes.
But at the same time, anyway.
But also because it's non-zero, only because there's zero momentum. That's analogous to.
Yeah, it's a little bit stretching of extrapolation of our usual knowledge, but okay, anyway, I'm fine. Thanks.
No. So next, let me try to discuss about the connection to the strong CP problem. So yes, so if we encounter the strong CP problem, of course the theory is depending on theta, and then this means that the vacuum energy can depend on theta, and then this SSB and strong CP problem is tightly coupled. So if you encounter strong CP problem, we seem to have a SSB of global minus one from symmetry. So how this makes sense? So this is saying that if we could avoid in some way this SSB of global minus one from symmetry, we could have a solution to the strong CP problem. This is naively indicating, and actually the axiom is nothing but the satisfying this condition because the axiom removes the pole. And yes, so topological solution is
Can I ask one question? So a strong CP problem is a question exactly for what value of a theta you have a minima. And then the notion of a spontaneous breaking of -1 form symmetry is the curvature regardless of where the vacuum is. Okay. How do you make that connection precise and rigorous? You know what I'm questioning?
So I thought that if the theory encounters some problem, the partition function is dependent on theta, or a genetic function theta regarded as some constant source depending on theta, and then the vacuum energy is coming from this dispatch function sum. So then this is related to the SSB minus zero.
I mean, if the vacuum B of theta before introducing axiom is in such a way that whose minima is at theta equal to zero.
Yes.
Presumably we don't have. Do we still have a strong city problem?
Also,
You still do, because it's not dynamic.
so
It's a super slab.
Uh-huh.
I think that what they were saying is the presence of the theta at theta already is a strong city problem.
Right. Okay.
Just rephrase the presence of the theta.
yes, depends the set one. Yeah. Yes, that's true.
Actually, so you're using the fact that if the fact that you see non-zero chi means that simply there's a theta dependency theory.
Yes, yeah.
Then it's sufficient to say that the theory has strong city problem. That's how you make a connection.
Yeah, so yes, and yes, that we want to say. But how sufficient it is I still need to consider.
Okay.
Yes, yes. Okay. So action is a solution, and also the massless quark solution is also this makes the theta is unphysical. So this is similar to the action solution. So this is also used for and another solution is the CP symmetric solution, but the CP symmetric solution case is still we have a non-zero topological stability, and then this cannot be understood in terms of this kind of condition. So CP symmetric case is this is still non-zero, and then yes. So we don't know that Nelson bar type model CP symmetric solution is having some understanding in terms of general symmetry stuff. This is we don't know. Okay, sorry. So far this is just a understanding of exist already know solution. So in 10 minutes, let me try to consider some. How about the explicit breaking? Because if we have naively, if we have explicit breaking, then the code might maybe used. So how can I get the? But first of all, I will say that this trial is failed. So if this doesn't work, but what kind of approach can be considered? Let me try to say. Okay, so first of all, what is the explicit breaking of minus one form symmetry? Because so this means I mean that the minus one form symmetry cannot be gauged. Or if we try to gauge this minus one form symmetry, we encounter some inconsistency. So there are several ways to consider the explicit breaking, but one thing is, suppose there is some mixed anomaly between this minus one form and the other global symmetries. And then if I gauge the other symmetry, then minus one form symmetry is explicit broken because we cannot gauge both symmetries simultaneously. So yes, actually this we have this kind of case. So let's go back to the 2D Maxwell theory. And we gauge the work of symmetry by introducing the now because of this BE two-home gauge field, so this theta cannot have a theta plus 2 pi. So this is the example we cannot gauge the minus one form symmetry. And then if I look at this theory, this seems like a Stuckelberg master, and then the pole seems to be removed. Oh, and then I'm happy if we can apply to this is QCD, but in QCD, we don't have any E13 form symmetry. So we cannot use this kind of approach to solve the strong CP problem in QCD, QCD or some yes, in the real world.
You do have a three-form symmetry, right? Because the C.
Yes, in low energy, yes, theory. I think yeah.
Okay.
But yeah, I don't. Yeah. At this stage, I don't. Okay. Also, I want you to talk about some explicit breaking by the monopole. Maybe I will move on to the quality problem. So what can we say about the quality problem? So okay. So this minus one form symmetry is global symmetry. So if I assume that all global symmetry must be explicitly broken or gauge, then this minus one form symmetry must be also the gauged or explicitly broken. For simplicity, let me first assume that every minus one form symmetry must be gauged. So if I remember that what kind of term is disturbs the original action potential, is that this theta is the original QCD1, but this theta may be coupled to the, for example, some dark sector, some SUN, or this theta might be coupled to the some original silicon field. But here I say that every minus one form symmetry must be gauged. So these are all minus one form symmetry. First minus one symmetry. This means if I require this, I need a gauge field for the to make all minus one form symmetry gauge. So I need to introduce 3 action, for example. Then this seems to that because QC action is only coupled to the so we have enough action and we don't need to care about the other sector. So this can avoid the quality problem. However, this is not only the source of so this is not only the source for the action potential. So this is something in mind that the action is coming from some higher form field. But if I start to consider the action some coming from complex scalar field, then some quantum gravity effect maybe produce this kind of potential, and then I don't know how I should consider. Yeah, even in this case, I could use this kind of requirement, but this is still strange, so I'm still considering. And also the explicit breaking, there's some, yeah. So if I start, so this is a quite big requirement. So if I start to consider also explicit breaking, so I still need time to sharpen this kind of argument.
Yeah, this is the same multiple polar problem proved by two-form dual formulation of axiom, right? So if you,
Yes.
so this is only zooming into that sense from the Poland problem, but you're using more generic version of the Poland.
Yes. Yes, I have still, I could only through the half of the I prepared. Well, thank you. Yeah, I think this is the time. So thanks so much.